Hello again, physics friends. We're going to talk today about Newton's second law, equations of motion, and differential equations. So Newton's second law we're going to start with right here. dp dt, the change of momentum in time, is given by the net force. And once you specify all the net forces, you then have an equation of motion. Okay, and that equation of motion is a differential equation. As we said earlier, if we're dealing with velocities that are small compared to the speed of light, and if we have a constant mass, then we can equivalently write the Newton's second law as the second derivative of the position vector times the mass, r double dot, is equal to the net force. And just as recall, momentum is m times v, derivative of v is acceleration. Assuming that the mass is constant, then we have this expression here. And we notice that this is a differential equation. It's a second order ordinary differential equation. So we call this an ODE, second order ODE. And why is it second order? Well, that just means that the highest time derivative, is the second time derivative. And what does ordinary differential equation mean? Well, it's not a partial differential equation. There are no partial derivatives. So we call it an ODE instead of a PDE for partial differential equation. All right, well, let's consider some case here, and let's start by talking about something that's easily solved in Cartesian coordinates. Okay. And just as a reminder, by Cartesian coordinates, we just mean x, y, and z. And what we know from previous videos is that the unit vectors x hat, y hat, and z hat are unchanging. So their time derivatives are 0. So what do we have? What are some examples of this? Well, maybe we have a box sliding along a floor with a velocity pointing to the right. This is one-dimensional motion, and we could make good use of Cartesian coordinates to describe it. And similarly, we might have motion on an inclined plane, and if you use this coordinate system, then that motion would need to be described using both x and y. But this is really one-dimensional motion, which indicates that we can still represent everything in 1D. We just have to use a different set of axes. So we're going to tip our axes to talk about that kind of motion, but it's still one-dimensional. So in these cases, we have our Newton's second law, but this is a vector equation, and the vector has 3 components in general, and we've chosen Cartesian coordinates here. So really this is hiding 3 separate equations, and each component must also independently be true. So in other words, we must have m times the second derivative of x with respect to time is given by the net force in the x direction, and we can repeat this for y and z. So we really have 3 equations here. Like so. Okay. Equivalently, we could write this as the mass m times this collection of expressions, x double dot in the x direction, y double dot in the y direction, and z double dot in the z direction, because this thing in square brackets is r double dot, right? This is r double dot. So that has to equal the net force as a vector, which is the net force in the x direction plus the net force in the y direction plus the net force in the z direction. Okay. A nice shorthand notation for this is to use angle brackets to represent the vector, which implicitly is describing all of the unit vectors, x hat, y hat, and z hat, in which case we have the following more compactly. Like so. So we actually have three separate ODEs, one for the x, one for the y, and one for the z direction. And in general, we're going to consider forces that might be a function of position, velocity, time, and so on, not just constant forces. So let's just do a few examples to make sure we understand how this is it's gonna work. And let's start with a free particle, meaning we have a particle that's feeling no force. So the net force is 0 on it. And if we're going to work in Cartesian coordinates, we could write the x, y, and z coordinates of the net force as 0, 0, 0. And so we intuitively know by Newton's first law that if there's no force, then this object has to move in a straight line at constant speed. So we already know the answer, but let's just make sure we can derive it appropriately. So let's start with the x direction, and we'll do the following. We'll start with Newton's second law for the x direction, which tells us that mx double dot is equal to the net force in the x direction, but we know that that is 0. So we have ma equals 0, or mx double dot is equal to 0. Well, x double dot is the derivative of the velocity in the x direction. So we see here that the rate of change of Vx with respect to time is 0. That's telling us that Vx is a constant. We can call that V naught in the x direction, the initial velocity in the x direction. Okay, but we want to go one step further. We want to find the position as a function of time, not just the velocity as a function of time. So what do? Well, if we know that Vx is a constant, we can write V as the time derivative of x. And the time derivative of x we could have written as dx dt. Okay, so on the left-hand side we have the time derivative of the position, and on the right-hand side we have a constant. Just refresh our memories, make sure we recognize that this is a constant. Okay. The same is going to be true in the y and the z directions as well. And so now we have this ordinary differential equation, and it turns out that it's separable. So we can integrate both sides with respect to time, and all of the x's are on the left, and then on the right-hand side we have just the constant v naught x. Okay, so we can now solve this differential equation. Dx dt is equal to v naught x, and we can do that by integrating with respect to time on both sides. On the left-hand side, we have the antiderivative of dx dt, which is going to give us back x of t with some constant. On the right-hand side, we have the antiderivative of a constant, which gives us v naught x plus some other constant. Those two constants, c and d, we can merge into one and express this as x of t. I dropped a t. When we integrated v naught, we get v naught t. So on the right-hand side, v naught xt plus some other constant, which ends up being the initial position at t equals 0 in this case. Okay, so we've solved Newton's second law in the case where there's no force, and what we found is that the position of an object increases linearly in time, and it starts at x naught, which is wherever the particle was at t equals 0. So this is equivalent to saying an object moving under no external forces, no net external force, will just move in a straight line at a constant speed. Okay, well, we've done an example with no force. How about a situation where there is a force, and the next kind of step of complexity is that there's a force, but it's constant. So this would be relevant for, say, motion near the Earth's surface, where we have parabolic motion due to the free fall and the gravitational force. So in this example, we could say our net force is equal to the force of gravity, okay, which is given by, in Cartesian coordinates, nothing in x, nothing in y, and minus mg in z. So specifically, let me draw a little diagram here to show the situation. We might have a ball And in this coordinate system, we'll have y going into the page. So we have x to the right, y into the page, z pointing up. And this ball is going to feel a net force, which is the force of gravity in the downward z direction. Okay, and we can take g to be, well, we're not going to use numbers at this point, but g is g is about 10 meters per second squared. Okay. All right, so let's turn to Newton's second law, which tells us that mr double dot is equal to the net force. This is a vector equation, and it has three components. In our choice of Cartesian coordinates, we have m times x double dot, y double dot, z double dot. That vector is equal to the net force. Well, the net force has nothing for its x and y components, and it only has a non-zero z component. Okay, so out of this come three equations. Mx double dot is 0, my double dot is 0, and then mz double dot, this is the interesting one, is not 0. Okay. Well, we've already solved these first two equations. We did that in the first example, and what we found was that x grows linearly in time, and so y also must do the same. Although the initial y velocity and initial y position might be 0, or different than each other, than the x coordinates, excuse me, both x and y will evolve linearly in time. How about the z direction? So the interesting new stuff here is happening in the z direction, and we can say z double dot is the velocity in the z direction's time derivative, which in this case is equal to a constant minus g. We can once again integrate dt, both of these. And we have the antiderivative of the velocity. Well, that's just going to give us the velocity. And if we did an indefinite integral, we'll get some constant. And on the right-hand side, we'll have minus gt plus some other constant. And so we can write this out as minus gt plus some new constant. And that new constant will be the initial velocity in the z direction. Why is that? Well, if you put in t equals 0, then the only remaining term on the right-hand side is that constant of integration, which tells us what the initial velocity is. Okay, so we want to go one more time because we want to find z of t. We want the position. So we need to integrate this one more time because v in the z direction is the derivative of the thing we want. Okay, well, we're almost there. Let's move up and start here. We can say dz dt, which is our velocity, is equal to minus gt plus v naught in the z direction. And we're going to integrate that again with respect to time. And when we do so, we find the antiderivative of dz dt is z of t plus some constant. And that's going to equal to minus 1/2 gt squared. The integral of t is t squared with a 1/2 plus v naught z t plus some other constant of integration. Great. So we can shuffle these things around, merge the constants of integration into a new one, and we find the familiar result that the position in the z direction is a quadratic function of time. It's equal to the initial z value, that's combining c and d together, plus v naught z times time minus 1/2 gt squared. Okay. And we could have solved this generically for some constant acceleration a, in which case we would have had plus 1/2 at squared. In this case, the acceleration a in the z direction is minus g. Okay, so this is no surprise. We've seen this before. This is the basics of kinematics in under constant acceleration in one dimension, and we see the familiar projectile motion result. So let's continue by considering some other forces, and or at least classes of forces. And here's another one. So we considered zero forces. We've considered constant forces. So let's consider some variable forces. And here there's tons and tons of possibilities, right? These forces could depend on position. So for example, a spring force, the force depends on the stretch of the spring. It's a position-dependent force. It could depend on time, like you push harder and harder on the gas pedal as a function of time. What is the acceleration of the car? And what is the position and velocity that results? Or it could depend on the velocity of an object. For example, drag forces. The faster you go, the stronger the drag forces. It's not necessarily time-driven, but it's velocity-dependent. Okay, so a time-dependent force, for example, might look like, in one-dimensional motion, an x force that looks like a constant times time. So this is a force that grows linearly in time. I'll skip that one for now. But what about a drag force? Well, that one could look something like the force due to drag might equal, and this could be a velocity, a vector force. So we could have a force that is proportional to v, but with a minus sign. So the faster the object goes, the stronger the force gets, and the force is always pointing opposite the direction of the velocity. Okay, well, why don't we work through this example? F drag is equal to a constant times minus v. And let's consider just linear motion that's horizontal. So we have the following scenario. We have some ground, we have a box, and that box is moving to the right, and so it's going to experience a drag force to the left. Okay, and the way that we've written this out, it kind of makes sense to use Cartesian coordinates. So how about we say our velocity we can write as Vx and then nothing in the y or z direction, and our drag force we can write as minus bv, but there's only one component to that force because our velocity is it's always restricted to the x direction. So we're just going to ignore the y and the z directions totally. So Newton's second law then is saying mr double dot is equal to F net. And in this case, our net force is the drag force. And furthermore, we don't have to worry about the y or the z directions. So of the three equations that are sitting under this Newton's second law equation, there's really only one that we need to worry about. Mx double dot is equal to minus bvx. Okay, well, remember we know from many times before that x double dot is the same as vx dot, which is that time derivative of the x velocity. So we can just reframe this as a first order differential equation for velocity in the x direction, like so. Okay. And in words, we can say, we seek a function v of x whose derivative gives you back v of x with a minus sign. Okay, so a function whose derivative is proportional to the original function. Okay. Well, that's a big hint. I mean, we can think of some functions whose derivative are proportional to the original function, like an exponential, and e to the minus t would have a time derivative whose derivative is proportional to minus the original function. So that's probably where we're going to end up, but let's see how we get there formally. You might notice that this is a separable equation. So what do I mean by separable? Well, we can go in and pull all of the velocity content to one side and all of the time content to the other. And so we have something that looks like this. I'll divide both sides by m. So on the right, I'll have a b over m. okay, and then I'm going to divide both sides by v. So on the left, I'll have dvx over v of x, and then I'll move the dt to the right. Now I understand that dv dt is a function, and you can't really treat the numerator and denominators as separate entities, but in practice, it is fine to think about it this way as small differentials, if you'd like, rather than the functions. And so what we end up with is we're going to integrate both sides, and on the left we have the integral of 1 over v dv, and we know that that is a natural log function. So we'll have on the left the natural log of v of x plus a constant of integration, and on the right, the integral of this constant b over m dt is just going to give us minus b over m times t plus a constant. And again, those two constants are going to be merged together into a single value. So let's continue on. We'll say natural log of v of x is equal to minus b over mt plus some new constant. Well, we're running out, so what should we use? We use c, we use d, how about capital E? So this is a new constant, E is equal to d minus c. Okay. But we want to find v of x, not ln of v of x, so we can exponentiate each side. And when we do so, e to the natural log of a function gives you that function back. Okay, so we get the velocity on the left-hand side, and on the right-hand side we have e to the minus b over mt plus e, which is e minus b over mt times e to the other constant, right? Because when you multiply exponentials, you add the exponents. And so this final piece here, e to the capital E, is just some other constant. So, and it turns out that if you put in v equals 0, if you put in t equals 0, what do you get? You get v of x of 0 is equal to e to the 0 times e to the capital E. Well, this first term, e to the 0, is just 1, so you're left with e to the capital E. So whatever's on the right-hand side has to be the velocity at t equals 0. So we can just replace that with v naught x. So when we think about, wrong color. When we think about vx as a function of time, it's going to be equal to the starting velocity v naught x times e to the minus b over m t, like so. All right, so we are going to continue to integrate and find the position as a function of time, but let's just pause here and take a look at this expression that we've just derived, okay? And let's just make sure we understand a little something about it, right? So if we plotted this, the x velocity as a function of time, we'll start at some initial value, v naught of x, at t equals 0, and as time goes on, we're going to drop, and exponentially decay towards 0. So at t equals 0, we have vx is equal to v naught x. We already did that point. And as t increases, the velocity gets closer and closer to 0. So let's consider the time t equals m over b, which was chosen because at that time, well, I made a little mistake here. At that time, t equals m over b, the velocity is v naught x times e to the minus 1, okay, which is about 0.37 times v naught x. Whoa, that's exciting. All right, so if I go over to sometime later, then I'll be about a third of, or 2/3 of the way down from the top. And we just keep decaying and keep decaying and keep decaying. So now we have a graph of the velocity, right? What do you think the graph of the position looks like, right? So we know something about, we have now a map of the slope of the position for all times. Well, what does the position itself looks like? So let's try to figure that out before we actually do any differential equation solving. Okay. Well, let's think about this. In the beginning, we start with a high velocity, and that velocity gets smaller and smaller with time. So we know that the initial slope is going to be steep for the position versus time, and the slope is going to flatten out as time goes on. So let's make an assumption here. Let's assume we start at the origin at t equals 0. Okay, so that puts us right here to start, and the fact that our velocity is high at that point tells us that our slope of this graph will be large at this point. Later on in time, our velocity is getting smaller and smaller, which tells me that the slope of my curve must be getting smaller and smaller as well. Slope of my position curve. So I can try to interpolate here by eye what my position versus time graph might look like. And here's my guess. Okay. So let's make sure that we get something similar when we do this analytically. So we know v of t and we want position. We know the velocity, we want the position. We know the velocity is given by v naught in the x direction, e to the minus b over m t. And we also know that the velocity is the derivative of the position. Okay, so is this separable? Is this separable? Well, yes, it's separable. Okay, we can have the x content on the left and time content on the right, and we can then integrate these two. On the left, we can write this as x of t plus some constant c1, and on the right, we have to integrate an exponential. Okay, so we have this this v naught of x is still going to be there, it's a constant, and then when we integrate the exponential, we're going to get a minus m over b, which will cancel the minus b over m that's in the exponent, and we'll have some other constant of integration. Okay. Now let's simplify our lives here and define beta to be b over m, and also let's merge these two constants into one. So when we do that, we'll have x of t is equal to minus v naught x over beta e to the minus beta t plus some constant. Now, you might be tempted to call this constant of integration x naught, but it is not equal to x naught. How do we find out what this constant of integration is? Well, let's say that at t equals 0, x at that time is equal to x naught. So in that case, we have to figure out what the initial conditions are. Let's try and see what happens. So if we put in t equals 0 into this equation, we will get minus v naught x over beta times e to the minus 0, or e to the 0, plus this constant. And that whole thing has to equal x naught. So what is the constant c? Well, it's x naught plus v naught over beta. Okay. And when we put that in for the constant in this equation, we find a position as a function of time that's equal to the initial position plus v naught x over beta times 1 minus the exponential. And we now have an expression for the position as a function of time, And let's think through this and make sure it makes sense. So let's consider this specific case where we start at the origin at t equals 0, which means our initial position will be 0. So in that case, x of t would be initial velocity over beta, 1 minus the exponential. Okay, and at t equals 0, let's verify that we indeed start at the origin. So when we put in t equals 0, we get 1 minus 1, which is indeed 0. So that checks out. And how about at t equals infinity? Well, as t approaches infinity, this exponential fades away, and we're left with a constant. So our position is gonna exponentially approach, but never quite reach this constant. So we can make a plot of this in the following way. We have time on the horizontal axis, and we have the position as a function of time. We know that we begin with a steep slope, and we end basically with this asymptotic value of v naught x over beta, and we're starting at the origin. So we need to connect these. We have this exponential rise, and then that function flattens and asymptotically approaches the constant value v naught x over beta. Good. So we have gone step by step through this process to find velocity and then position as a function of time for a force that is velocity dependent. In fact, our force was proportional to velocity. You could also consider forces that are proportional to velocity squared or to time and other variable forces. And we'll have chances to look at those elsewhere through this class. But for now, let's wrap up here. We've focused today on how Newton's second law is a differential equation, and we've looked at how to solve those differential equations for various types and sets of forces. Zero force, constant force, and now we did one example of a variable force. So until next time, take care and be well, and I'll see you in the next video.